About 10, 12 years ago, I visited Professor Christoph Brockmann at Aachen University to make some trials with him and his team on the SPS equipment they had. At that time, they could make components about the size of a coin. But it was interesting because we could make special alloys that was difficult to make with traditional technologies. Therefore, I would like to learn more about what has happened with the SPS since I was in the lab with Christoph. And this episode is with the company CalNano, who has specialized in SPS. And I was shocked to learn how big and how complex the process has gone over that period since I was in the lab. You will be amazed. And I think if you look at my face during the episode, you can also see that I was pretty shocked. So enjoy this and learn about SPS and what it can do, because it's bigger than a coin today. Hi, Chris.
Well, hello, Peter. How are we doing today?
Fine. Thank you. And welcome to the podcast, Everyday Metallurgy.
Well, it's a pleasure to be here, and thank you so much for the invite.
Chris, we're going to talk about technologies that are called fast field-assisted sintering technologies. And I previously had one of these technologies on an episode with Alexander Weiss from the company EPOS, working with electrocenterforging. But today we're going to look into the technology called SPS, Spark Plasma Sintering. It's one of the old boys in the class, where the EPOS is one of the new guys. And I think we need to have the fundamental with us on board to understand really what is possible in this field of processing. But first, would you give a short introduction to yourself, your company, and what you do in your daily life?
Yeah, no problem. Well, my name is Christopher Melnyk, and I'm currently the Director of Business Development at California Nanotechnologies. I actually have a seasoned tenure at CalNano. I was actually the very first employee of the company back in 2006. When we spun off from a sister company who had commercialized metal matrix composite materials in a forged format for some track and field and aerospace applications. And then CalNano was formed as a kind of branch off of that with the intent of developing and commercializing next generation nanomaterials or advanced materials that could be integrated into very well established high volume production techniques like the progressive cold forging. So our job essentially as a company was really to help spearhead these new materials and find applications for them in everyday life. And so that's how we kind of started. And after a few years, I became CEO of CalNano, and then I hired most of our current executive staff, and then went on to buy and sell into a coatings company on the east coast of the USA in North Carolina, doing ceramic coatings as well as fluoropolymer cross-link polymer coatings. And then now I've rejoined the forces at CalNano and helping continue the adaptation of our two core technologies.
Fantastic. Thank you. So you are really the right person to ask. Could you give a short overview of the field-assisted sintering technologies? Well, what are there out there? It's not only SPS. There are also some others.
There are, and actually, as I'll pull up a diagram here so I can start showing. Please let me know when you see that.
It's perfect.
Perfect. And so I guess, you mentioned one right out of the gate, which is kind of new. And it's funny because I guess perspective and context is everything. So, you mentioned the EPOS and Alexander's technology there with the rapid discharge. Really wonderful, very much cutting edge on the, new in the same family, but very new. A lot of advantages to discharging very quickly for the very short times. Some limitations related to the, conductivity of the material and some other things, geometry, scales, things like that. SPS is funny funny because you referred to it as the old dog, which is not untrue, the old boy in the room.
Yeah.
But what's funny is that in industry, and especially in North America, it's actually still very much kind of on the forefront. So we still experience a lot of people who view SPS as, some new fancy lab thing that, hasn't really taken a foothold yet. And I think that that's different levels of true depending on where you are in the world. So early on, we adopted this through need. We were hot isostatic pressing everything that we did for our developments, which is a wonderful technology also, but it just was very slow. We had to put dedicated cans because the powdered material would be put into a canister and then evacuated and then, pressed. But it just took a long time, and then it was costly, and it wasn't very good for research. So, and at the time, we were also pursuing the maintaining nanostructures. So through our other technology, which maybe we'll get into later, we were cryogenically milling things, and with the intent of producing nano-grained, high-strength alloys. And that was, something given to us by Pratt & Whitney Rocketdyne at the time. And so then we were putting all this time and effort in making these nano-grain materials, and then destroying them somewhat by applying too much time and temperature through the hot isostatic pressing.
So it became micro and not nano.
Exactly. And so then we said, well, what's the best way to keep nano grains nano and consolidate these things? And that's what led us to SPS. And so we were one of the first adopters in commercial adopters in our area at the time. And since then we've gone on. So there's not too many competitors. I think one way it's described often is a fancy hot press, because essentially there's a lot of similarities, but obviously some stark differences as well. So as I'm showing here's the basic layout of FAST, and of course we use FAST and Spark Plasma Sintering interchangeably. There's probably 4 or 5 different names for this technology, which actually has not helped its adaptation very well, because I understand the hesitation and the different names, but from a commercial perspective, all the literature and publications are now spread across different terms. So when people are looking into it, they often don't find all of the information because different groups are calling it different things. But essentially, the main layout here, if I can get my slide to work. So essentially, this is the most basic layout. And confirm that you do see the video playing here.
Yes, it runs.
Perfect. So in here, basically, we're going to take our powdered material, but again, not always powdered. And then it's going to be in an environment where we pull a vacuum and apply inert atmosphere. And then we're going to compress the material uniaxially. And then we're going to pulse current directly through the material itself. Now, there's always a fun thing. I'll pause the video right here. These little sparks that you see, these don't exist. And so the name Spark Plasma Sintering is probably the most accepted name. It's between that and FAST. And I think basically what happened, the best I can understand, is that somewhere in the mid 90s, if you're densifying, say, aluminum as an example, aluminum particles, and you have these nice spherical particles, if they're passivated, they're going to have an oxide layer on them. And so, the aluminum is sitting there and it's got a nice oxide, like an eggshell on the egg. And then when you go to hot press something like this, the temperatures that you're processing aluminum are much lower, obviously, than the stability temperatures of aluminum oxide, which is a much higher temperature ceramic. So you end up seeing all those previous particle boundaries in your final consolidated, component. You would end up seeing all these nice eggshells touching each other, and the bonding between the aluminum oxide and the aluminum oxide is often insufficient when you're only processing at aluminum temperatures, 500, 600, in that range. So that's a perfect place for a crack to propagate and to, have a failure. So when they started SPSing, they noticed those oxides were gone, and we were getting great interparticle bonding. And so I think someone speculated that to get rid of that oxide, there must have been thousands of degrees. And since this whole thing is done in a vacuum and there's a potential difference between the top and bottom, and we're applying a discharge, that's a recipe for plasma, because that's, in a vacuum with a DC voltage, that's how you make plasma. So I think someone speculated that must be the mechanism that's removing that oxide.
Of course.
But I think that's been pretty settled that's disproven. And really what we're happening here is just a very localized Joule heating. Just resistive heating going through the material in most cases when it's metallic components or metallic powders that we're playing with. But also there's the field part. And so because we're pulsing, and that pulse conditions can change, and sometimes it's just direct, so it's not always pulsing. But in the cases of the pulsing especially, that change in current is what's going to generate the magnetic field, because whenever there's a change in electrical current, that's when you get that. And so every time you pulse one of these currents through, you give it a magnetic field in the area, which provides an additional effect to the sintering. So that's true even in the case of non-conductive materials. So there's still advantages to be had when we're sintering non-conductive materials as well. And it actually.
When you, I thought you needed to have conductivity of the material. So when you don't have that, if you have a ceramic, will you introduce the heat through the die? You heat the die instead.
Absolutely. So in that case, oops, and sorry, my slide jumped ahead there. In the case that you mentioned, yes, the heat is not as central. The heat is coming mostly from the die to start with, as the current will go through the die, and that sneaks ahead to most of the time the tooling is graphite, not exclusively, but in a lot of times it is. So it is a conductive path as well. And so, and then sometimes it's a hybrid, because in some cases, like aluminum oxide being a good example, it becomes more conductive as it gets hotter. So, its conductivity starts off as an insulator, and then as you heat it, it'll start to absorb some of that current density through it as well. So in that case, it is the die, but it's still an intimate contact with the part. And so if you compared this with, say, hot pressing, where you have heating elements way out here and it was separated with a vacuum, that's not exactly an ideal way to get heat to transfer into your die set. So you'd have to have a heating element, which could have a maximum temperature. Then you have a gradient, and that's radiating, and then that heat has to be absorbed on the outside of the die and make its way into the inside of the die. And so those processes typically take like 12 hours, long, depending on the material. It could be, into the days sometimes. So the main advantage here is that we are applying that pressure and then that current directly, again, either directly to the material or just to the die outside of it. So that's the basic premise of the SPS, and that allows us to get a whole bunch of special advantages, which we can get into as well.
So what is the pressure? Are we talking several tons per square centimeter, or?
And that's another thing that you'll find differences. So that's heavily dictated by the material needs and also the tooling. So you'll see some research paper on some more niche applications where they have carbide tooling or silicon carbide tooling that has wedge shapes that's really concentrating, and then multi-wall dies that can really take much more pressure. And those will get into the gigapascals of pressure. But that's really the exception. The vast majority is sitting in the 20 to 50, maybe 80 MPa pressure ranges. So of course, the applied force, it's a mathematical number there.
It's in standard powder compaction. It's typically 500, 600 megapascal. So it's in the low range.
It's in the low range compared to like cold pressing.
But also the tool,
absolutely.
if it's a graphite tool, it's difficult to press that hard.
Exactly, and tooling failure would inevitably happen there. So, and the difference here is, typically in cold pressing, you're using tool steels. They're very strong. You're basically just trying to keep something in a green form. So it's just a different animal. And in this case, we're getting the density, our desired density in one step. So we're press and sintering all in one step, typically. But it's very flexible, and that's another kind of important part with this, is that it's so flexible, and that's one of the main benefits that we have is in some cases we're starting with green pressed parts. In some cases we're starting with solid metals that are already solid, and we're just bonding them to other materials. And sometimes we're bonding powders to metals. Sometimes we're bonding ceramics to other ceramics. So it's so flexible, and there's no maximum or minimum temperature. We can put thermal gradients in on purpose. So if you're doing a monolithic, component, you would want temperature uniformity, and of course then we have ways of achieving that. If you wanted to make what would be called a functionally graded part, where you have say a ceramic on one side and a metal on the other, you might desire, even if you have to do that in multiple layers that are all bonded together, you might desire a higher temperature and a lower temperature from one part of your component to the next. And that can be designed in SPS because we have current density to play with, so we can design asymmetrical tooling, which would get hotter in one area than in another area, which is another advantage. You can't do that in a hot press necessarily, because
that's pretty difficult. How long time does it take one press?
It's a good question. So again, very dependent on what you're doing and the size. And so people will read literature and see 5-minute sintering times and 10-minute sintering times. And that's true, and we do that. I would say the average is probably hold times are typically between 10 and 40 minutes is kind of a general spot where
Mm.
most materials fall.
Yeah.
Are some faster? Yes. Are some longer? Also, yes.
Yeah.
That's typically tied more to the mass and the size that you're dealing with. So as your component
Mm.
gets bigger and bigger, the die and the tooling gets bigger and bigger, and that
Yeah.
starts off at
Mm.
room temperature typically, and so you have a big thermal mass. And so if you try to heat up the part in the middle too fast, it's sitting inside of a nice big large heat sink, so you'll end up
Mm.
with horrible heat gradients, and there's really just not a good way to solve that other than preheating the tooling, and then there
Mm.
are some equipment manufacturers who try to deal with that by putting in hybrid systems where they'll put induction heaters around the die so that you can apply induction heat to the die, while
Okay.
you're applying direct current through into the part, so
Yeah.
that you're having you're helping
Mm. Yeah.
eliminate that lag.
Mm.
So
But
yes, it really depends.
these minutes, they are the active period. So do how long time does it take to set up and dismantle again?
That's also a good question. So, it really depends again. So, I have to be careful what I share on whose technologies and what, but similar to, I've seen as advanced as cold pressing in the same fashion, where you have double acting presses that have been
Yeah.
outfitted internally, where you can have sweepers, powder goes in, so it's all done automated, and you can press and sinter the part completely and then extract
Mm.
it, shift it over,
Wow.
and move on. So that's as fast as you could possibly be,
Yeah. Yeah. Yeah.
obviously. But of course, the setup time and the infrastructure to have that is also, more in depth as well.
Yeah.
So I would, again, it varies because sometimes we do very complex things sometimes where we have components being produced in situ, where we're making like an actual component that has heating or
Mm.
cooling passages or components centered into it all in one step. So those take a little bit more to set up, obviously, because you have
Yeah.
to support those structures and do various things.
Mm.
A very basic setup, just a few minutes. It's as
Mm.
simple as pouring powder into a cavity. The die has to be typically prepared. We
Yeah.
use different types of foils and liners to aid in separation for the detooling portion of it. We
Mm.
use various sprays as well to help in that case.
Yeah.
And that can also be used to help control current in different ways to
Mm.
increase or decrease those hot spots, as we mentioned. So yes, to answer your question, yes, I was talking about active time. I was talking about hold time. So that was just at the top of after you've ramped up, your hold time at your
Mm.
maximum temperature. That
Yeah.
was what I was referencing. But the same applies to the ramp rates.
Mm.
So people will read, on the small scale, you can do a lot of cool things. Similar to the EPOS discussion. In small
Hmm.
scale, we can ramp up 300-400 degrees a minute, and then ramp down very, very quickly as well, because it's just a part of it. But as you get larger, those ramp rates start slowing down into more
Yeah.
reasonable speeds, like
Mm.
like 10,
Yeah.
20, 30 degrees, on the high end as you approach
Mm.
the holding temperatures.
Yeah. And you showed just before with your
Hmm.
hands sizes like this.
Yeah.
Uh, I've only seen this in lab scale. So we talked a coin in size.
That's
But
funny. So that's a funny one. When I departed CalNano for a while and came back, we had just purchased our first SPS, and I was running that one at the time. And so yes,
mm,
its maximum size was about 1 inch, a 25 millimeters
yeah.
type thing, and that was common, and that was a common issue. I'd be at a trade
Mm.
show or at a conference trying to sell this technology as the next
Yeah.
thing. And so people would always
Hmm.
say, well, yeah, I've heard it, I've read the papers, I'm interested in all the advantages, but I need to make something bigger than a button, so I'm not
Yeah.
interested.
Yeah.
um that's one of those misnomers. So now, fast forward, California Nanotechnologies has 4 SPS units, that range from capabilities as small as a few millimeters all the way up to 300 plus millimeters. And so,
Wow.
yeah, we have the largest commercially available SPS tool in North America, and that's actually
Mm.
made by Dr. Fritsch out of Germany.
Ah.
That's called the
Yeah.
MSP5.
Yeah.
It's a wonderful machine, and yeah, we love that. And so we say 17 inches, of course, American
Mm.
units. But yeah, 300 plus millimeters is kind of the range there. Um, and of course, that's also dependent on the material you're doing and the pressure you need. So it's a 500-ton press with 85,000 amps of current. So
85,000 amps.
85.5 actually, but yes, yeah, over
Yeah,
85,000 amps of
yeah,
applied current. Yeah.
yeah,
So you need it's not a small amount of energy, that's for sure.
yeah. You have emptied the country for copper.
Yes, now that is the amperage that's applied at low voltage. So that's very important to
Of
note.
course, yeah,
Obviously, amperage
yeah.
and voltage
Mm.
relationship, but um, so I think it's like 750 kVA is kind of the
Okay.
transformer I think that feeds that
Yeah.
thing plus or
Hmm.
minus. So yeah, so it steps down, and that's another. We mentioned it earlier. There's different manufacturers around the world. So our first one, we became an actual official supplier, was for Fuji, and then now Suga SPS out of Japan.
Mm.
And there's a few Polish manufacturers now that also have some AC systems. Dr. Fritsch has an AC system on their LSP 100 now, where they can have an AC sintering. So the technology is expanding. There's
Mm.
different advantages, high voltage versions now that are up in the hundreds of volts versus the
Okay.
all of our systems typically operate
Mm.
between about 5 and 10 volts
Yes.
is a typical voltage.
Yeah.
So amps come easy when you're at low DC voltages, but
Yeah. But how do you make it high voltage? Do you change the dye material to less conductive?
no, I think it's on the power delivery side of things. So, we don't have one of those units, so I can't speak too much about it.
Okay. Yeah.
But yeah, it's just the desire on how you do that, and same with the pulse
Mm.
conditions. And so, like, there's on-off DC, square wave, sinusoidal pulses. So
Yeah. Yeah.
even just in the delivery of DC, there's a few options that
Hmm.
sometimes have no effect, sometimes have some significant
Uh,
effects.
you can run
Um,
it in burst mode or cut it,
Exactly.
things like that.
Yes.
Yeah.
Yeah. In
Hmm.
a kind of quasi version of the EPO system, you can do like a capacitive discharge, just build it up, and not quite to the same extreme level, but you can flash sinter as well.
Yeah.
And a cool effect, if you haven't been around one of these machines when they're pulsing, is if you hold a rare earth magnet in your hand anywhere near the
Oh,
machine, it shakes in your hand just, yeah, as you're holding it, because the magnetic
yeah.
fields. Exactly. If you hold one of
Yeah.
those in your hand when you're around the machine, it pulsates in your hand. It's a
Yeah.
cool effect. Yeah.
Yeah. I could imagine.
Yeah.
So no pacemaker nearby.
Exactly. Exactly.
Yeah.
Yeah.
Talking about energy, energy is a big factor these days.
Yes. Yeah.
Is it a high energy consuming technology, or
It,
as you do it this fast, do you use less energy than you do with the hip,
Abs-
for instance?
Absolutely. And so I don't know, I haven't seen any specific comparisons with hip, but I have with hot press. And yes, and actually I'm
Hmm.
glad you asked that, because
Yeah.
especially for our European listeners, because
Mm.
yeah, the more importance, and it is also in America, for energy, and in the rest of North and South America as well. But yes, our friends at Idaho National Laboratory, Dr. Jorgen Ruffner over there, they did a nice little study where they found energy savings of 91% savings of total energy spent making a high temperature ceramic. I believe it was silicon carbide. Don't quote me on
Hmm.
that, but something
Yeah.
in the 2000 degrees Celsius range for
Mm.
pressing, and they found a total
Yeah.
energy savings of about 91%. And so yes, and that
Mm.
comes from the shorter cycle time, the faster ramp rate, and then the faster
Yeah.
cool down. So yeah, it takes energy, but so does heating up resistive
And
elements
and I
for
guess
hours and hours.
also, if you have a bigger system, you need to heat up the entire system, the walls and the furnace and the heating elements.
Exactly.
So you have a lot of dead weight
Exactly.
with you that you have to heat and cool.
Exactly. And the
Uh,
time, right? And like I said, that really extends it. But
mhm.
absolutely, yeah, you're heating up this big box for all this time, and why, we just heat
Yeah,
up the part ideally, okay, the tooling around it, and that's it,
yeah,
and everything else is
hmm,
kept cool.
exactly. Yeah, yeah.
Mhm.
Uh, so listeners, they would say now, I could use SPS for everything, but where would you say SPS is not applicable?
Just like anything, because I don't know how to describe it. Here's some energy savings right here. Actually, we're just talking about that. Yeah, any
Mm.
sense? Anywhere where how to explain it, other technologies that have matured and had decades and decades of optimizations around them, there's lots of cool things that can be done where you don't, if it can be done another way that's very commercial and high volume, then then it's probably the fine and good way of doing it. So it's hard to, don't spend too much time thinking of the things we can't do, but there are definitely applications where there's nothing to be gained. If you're not looking for a complex shape or a difficult to sinter material, or you're not trying to do it faster, then maybe. But if it can be hot pressed, it should probably be fast, SPS, because if there's a reason for it to be hot pressed, that same reason probably validates the effort. If you could forge it or cast it, and it's a large complex part and casting is sufficient, then that's probably the way to go. I mean, because castings are very cost effective. You can do that. We're not going to probably beat that in throughput or scale or complexity. So if it can be cast, go ahead and cast it.
And I guess also if we talk about standard steel components made in powder metal, the present center, you cannot do anything that makes it better. Making with SPS,
not with standard materials. So typically in the world of press and sinter, where that overlays with us would be like the request we see is when it's a size limitation. So one area would be, for instance, in the soft magnetics when you're press and sintering, and that's more related to the pressing side, because as we mentioned, the cold pressing is so high, but getting uniform pressures on complex geometries to get uniform green densities, and then also maintaining a final sintering geometry that makes sense, that becomes difficult. So most people have a limitation on size on what they can do in the press and sintering, where we don't have as much of a limitation there. So that's one area. The other one would be just material selections that's not standard. If you're going to a material that just is a bit outside of the envelope of what's established in press and sintering, then that would be an example as well. So just because we don't really have any material limitations.
No. So if you should mention what kind of properties are the core properties you could get out of an SPS material. So why should I choose SPS for this?
Yeah.
What does that give me, and what kind of materials will that be?
It's a great question. And so typically that's going to be it really, again, there's many different answers. And so like I mentioned earlier, for us, the early driver was to maintain nano grains or fine grain structure. That segues very closely into just more control over your crystal structure and your grain structure. So if you have some sort of metastable phases that you want to maintain in there, if you want to avoid formations of some sort of like intermetallics or undesirable phases,
because you are so short in time, so segregation doesn't occur.
Exactly. And so it gives you a lot more control on the up and down and total time. And so often, it can be on both sides. And actually we have a project right now where that's kind of the issue is, there's a temperature region that's well within the densification where you're going to start forming, some undesirable phases. And then if you go above that temperature, then you can start dissolving those undesirable phases. And so, the job becomes clear that you need to get up, avoid time in that area on the way up, and then, avoid time on that way down. But being able to do that is really the advantage in this case. So those are the types of properties. The other ones are the, like I said, multi-material systems is a big one. When you're trying to bond different materials, we see a lot of work there. So sometimes it's just the same components, just the same material, but just with like some physical channels or some properties in them. So say you take a block and you can make like a few micron wide channel that might be a cooling passage or something. Then you can take another plate and diffusion bond it, hermetically seal it completely together without any brazing materials or any kind of bonding materials, and maintain that passage being in there. So you could imagine the advantages for something like that. So and then we get into complex geometry as well. So you can do much more complicated geometry than you might think.
Yeah, I could see on the photo you showed before. I have a case, an alloy that has often been mentioned in not for SPS as what I know, but for other application, is aluminium with high silicon. So an over eutectic. Because if you try to cast it, then it will just segregate when
Yep.
it solidifies.
Yep.
So I have seen that made with powder metal and with spray forming.
Yep.
Could that also be made and secure very fine grain in the SPS? Is
Absolutely.
it
Yep.
an alloy being made? Do you know?
I can't think off the top of my head of specific examples that we've worked on.
Mm,
So I can't say like, affirmatively yes, but yeah, but the concept absolutely. That's exactly the kind of benefits that you get, if you're looking for
yeah.
something like that.
Mm,
Mm,
mm. Uh, and when you compact, when you make standard pressure center, you can reach density 90%. If you go MIM, you can reach density 99. If you go HIP, you get 100
yep.
almost.
Yep.
Well, where are we with SPS?
Yes. I say that because all of the above. So the one beautiful thing about SPS is that you can control that very precisely and repeatably. So sometimes people will come to us when they have a material that they wish they could get to a higher density, but their current path limits them at 90%. We can
Mm,
get it to 98%, in a hard to sinter material. So it's
mm,
always better. And then in some cases, of course, I never like to say 100% because there's
mm.
always a micropore somewhere. Honestly, 100%. Like and often sometimes we end up with materials where we do Archimedes and 3D scan them and they end up over 100%, and we
Mhm.
have to go back and obviously question the theoretical density of the material to start with. So
Yeah.
yeah, but we can go all the way from 100% all the way to very low density, which is
Mhm.
sometimes desired as well because we can stop the applied pressure and then keep the temperature
Mm.
up and
Yeah.
leave open porosity. And
Yeah.
so we can use SPS as a surrogate for other processes. And some of our
Mm.
customers, like in the hipping example, have come to us and said, well, we already know that the final product is going to be done in hip, or it's going to be done really large. That's kind of set in stone for whatever reason. But we
Mm.
don't want to go through and do 100 experiments trying to figure out
Mm.
the right alloy or the right this and that. So even though SPS can do it faster, we actually don't want the advantages of the shorter time. We don't want the
Mm.
advantages of all that. We just want to make lots of samples quickly. So we can actually just use the SPS to like hold the temperature longer than needed, but it's still much faster in general than
Mm.
going through the canning process and all that and doing all that.
Yeah.
So we can use it to kind of mimic other processes. We can go
Mm.
hotter than we want. We can actually put pressure on just the die and
Yeah.
leave an empty cavity, and then use the SPS as a pressureless sintering vessel and just create a
Mm.
very small oven that has field assisted around it.
Yeah.
And
Yeah.
so now
Yeah.
you have no applied pressure,
Mm.
but just the temperature and just the field,
Yeah.
and you still get some advantages there too. So
Mhm.
it's a very flexible tool
Yeah.
for a whole bunch of different applications.
Yeah. Mm. Um, and then you also told about this the nano part,
Mhm.
and uh, I am curious to learn a little about how you make the nanostructured materials. Can you tell a little about that?
Yeah, absolutely. And so often our customers come to us with their own materials. So they've synthesized them, any number of different ways that might be the case. But internally, as
Mm.
I mentioned earlier, yes, our company actually started with the powder side and then got into the SPS as the second thing.
Yeah.
And that was through a process called cryogenic milling.
Mm.
And so the cryogenic milling, in our case, there's many different types of ball milling or milling in general. So people are
Hmm.
familiar with, you take a vessel and you just put
Yeah.
beads in there essentially and you tumble it. And that would be like the
Hmm.
most fundamental kind of low energy version of milling. Same
Mm.
logic, takes long, long time.
Yeah.
Energies are really low.
Yeah.
Works.
70 hours or more
Yes,
sometimes.
exactly.
Yeah.
And that's fine. Cryogenic milling, and actually let me share this again for you.
It sounds cold.
It is cold. Yes, exactly. And it's funny when I first heard about this before I got into it, mechanical engineering background. And so when I heard cryo milling, I thought like machining, like milling, and somehow you're doing
Yeah.
this under some sort of liquid nitrogen. I was like, why would you do that?
Hmm.
No, couldn't, nothing like that. So here's the basic setup. Obviously it's an illustration, but we have
Mm.
a vertical, in our case, vertical shaft with an arm in it and a very high amount of torque and rotational energy being imparted into a vessel that is
Mm.
full of grinding media. Now that could be tungsten carbide, it could be stainless steel. Typically, we use just hardened stainless steel. It's a good workhorse for all this. And then the material you're going to process is already powdered in this case. And then we completely cool it down to cryogenic temperatures and then mix it often, not all the time, but often completely mixed with liquid nitrogen or liquid argon. So it's in a slurry. And then it's being ground, and then we're adding more liquid nitrogen or liquid argon, and then there's some being in the jacket to keep it cold. Exactly. And so as that milling is happening, depending on the type of material, different things will happen. But here we can see, if it's a brittle material and it's a large particle, it's going to break down because it's just brittle and it's being broken down. But if you do this not cryogenically with, say, like a soft alloy, like an aluminum or something like that, it's going to cold weld. All that material is going to weld itself together and it's going to gum up. And so the cryo helps embrittle it. And then we also use some process control agents to further, prevent the material from over agglomerating. And that's actually when you start to get the refinement of the grains. So essentially kind of like making saltwater taffy, if you're familiar with that process, where it's folding and blending over itself over and over. So you get this like very thin layer, and the powder is actually a coating that's being formed on all the media. And that coating is being formed, and those particles are being mashed and smeared with extremely high deformation onto the metals. And then that coating breaks off and then becomes powder and repeat and repeat and repeat. And so, and that's how we're actually able to produce nanostructured materials. And in the case of the metals, we actually prefer to not make the particles nanoscale, but just the grain structure, so we can get the properties of the nanomaterial that we want without all of the safety and pain and reactivity of nanoparticles. Which
I could imagine that if you have a metal and you make it in nano powder and you take it out in air,
it's pyrophoric.
It would like to burn.
Yes, and we have a patent actually around being able to do this safely and efficiently because of that exact problem. So I've had the wonderful experience of seeing some metal fires myself, and this stuff can be so, like titaniums especially. Everyone's worried about magnesium and aluminum with good reason, but even titanium seems to be very pyrophoric when you do it, and so. It literally just ignites immediately upon contact with air. It doesn't need a spark, doesn't need any heat, doesn't need anything. It's just like there's a fog coming off, and in that fog there might be a little particle, and it just sparks like fireworks constantly when it's coming off. And so if you dump that material, it's in a liquid nitrogen slurry, so it's safe right now because it's cryo cold and there's a protective layer of nitrogen around it. As soon as that nitrogen is boiled off and there's none left, it's like a fuse, like you have a certain amount of time. And so but in that, focusing on the nanomaterial production side, that's it. And that's also how we produce novel alloy systems. So in the early days, the focus was heavily on producing nanograins. And here you can see like a typical conventional particle size, 5 to 80 microns. So nothing special on the particle. If you cross-section one of those particles, we have a very nanostructured grain structure. And in this case, ex situ added ceramic particles that are uniformly distributed throughout the particle as well. And so sometimes those might be formed in situ. Sometimes we might be adding those as dispersoids or adding things in there for various reasons. They could be grain reinforcements, stiffening agents. They could be there for preventing grain growth later on. So whatever that might be. But nowadays we have a lot more focus on just creating new alloy systems, going past solubility. You mentioned the silicon eutectic or hypereutectic. Similarly, we do a lot of work these days in high-entropy alloys, novel refractory high-entropy alloys, because we're not limited by the solubility limits even. So we can go even further than that because, the classic example is you can only add so much sugar to your water before eventually it stops dissolving and it just settles at the bottom. Sure, you can heat up the water, get a little bit more in there, but eventually that's it. But if you start off with snow and ice and you're working in a freezer, you can mix any ratio you want and blend them, and you could have 80% sugar if you want with uniformly distributed water in the form of ice. And so that's, we're not limited. So we can add whatever ratios of whatever materials, and we're never going to melt them. So we're always going to compress them, and then we're going to sinter them. So we're going to end up forming, and so we form solid state alloys in the powder form. And that also applies to adding of those ceramic particles. So if you're making metal matrix composite or oxide dispersion strengthened material systems, often the ceramic that you're putting in there is not going to be the same density as the metal matrix around it. It's either going to be more dense or less dense. And so if you were to put that in a liquid, those particles are going to settle, or they're going to sink, or they're going to float. Again, we don't care because it's all powder. So it's all being milled. So we get to uniformly distribute those and then freeze them in place before they have a chance to stratify and fall or rise to the top. So we can embed them necessarily. So yes, that's probably what we do most of now. And again, we're able to produce new alloy systems in a day. So we can tweak. So one of our customers, as an example, we do 4 alloys every week and make them into samples. So they have a design of experiment of all these different chemistries they want to evaluate. And so we try 2%, 3%, 5%, try a little addition of this, whatever it is. Yeah. Make a small sample, go send it for testing.
Yeah. It sounds like when you do that, you are making few grams and not kilos, but you might surprise me again now with size.
Absolutely. Yeah. So our smallest R&D scale, we can go down to 500 grams, but that's really on the low side. So our typical starting R&D run is 1 kg. And then we have various mills that go all the way up to, about 50 times that. So the typical workhorse is probably in the 25 kg batch range. Yeah. And again, that depends because the amount of balls, the way I had that picture there, the amount of media to ball ratio is going to dictate. There's a volume limit in there. So the density, the tap density of your material matters. If you're processing tungsten, you could probably fit 100 kgs in the bottom half of that mill. When you're processing magnesium, it's probably
it's a lot less.
Yeah, it's a lot less. So so that affects. And then of course the ball to weight ratio is what we call that. That has a huge effect on everything else as well.
Yeah. Often when I have seen ball milling, there's also aware of the balls, meaning that you make a false alloy or you make some pollution of the alloy with your ball media. Does it also happen here when you're on cryo?
Sometimes yes, sometimes no, and sometimes a little bit. So, and the reason for that would be, again, remember that coating I mentioned? So not every material does that. So the materials that coat, the answer is more of a no. And there's two reasons for that. Because we do a break-in run, we call it, and it's essentially like a seasoning. And so the first amount of material we put into the mill, once it, we start off with the mill's been fully cleaned, everything's fine. Then we put that coating inside of the mill, and then the excess material that's in there is discarded, and that's like the break-in material, and that's not that would be your contaminated material. At that point, all of the hardware, the arm, the bowl, the balls, all have a coating of your material on it. And then when we add the material that we're now processing, it's never actually in contact with the milling media because it's always building up and breaking off that coating. So the contamination is very, very little. Of course, I'm not going to say never possible at all because, there's always a chance that, a little bit of an arm or something, depending on the material. And then that's further intensified or reduced by the hardness, obviously, and if you're adding ceramics in there and you have essentially an abrasive grit, then of course that's going to intensify it. If the material doesn't form the coating at all and it's just a pure ceramic and you're just trying to break it down, well then of course that's a different situation as well. So if you're grinding a hard metal that doesn't agglomerate, and then you're more likely to, and then that's when the hardware selection becomes more important, and maybe moving up to like zirconium or tungsten carbide for your milling materials to beat it with hardness, and or find a compatible material, or remove it after if you can, if it's like magnetics. So we use mainly magnetics, so you can remove it. But of course, if you're making a ferritic material, then that becomes no longer an option either. But yeah, generally speaking, it's not a big deal. There's many products we cryo-mill that have an iron limit, and after milling a while, we pick up a little bit, but it's usually well within the acceptable limits.
Perfect. Chris, we have talked a lot about theoretical stuff, and I would, in the name of Everyday Metallurgy, I would like to learn a little more about where do we see this in our everyday life. what would happen if SPS didn't exist? Would my car disappear or uh,
Yeah,
w-
yeah, it's a good question. I don't know if your car
yeah.
would disappear. And there's often a lot of things where there's an old way and a new way, and the old way maybe just isn't quite as efficient, or maybe,
Mhm,
a new
mhm,
material is now available. If you remember,
yeah.
we all used to have cell phones where the screens would scratch in,
Hmm.
no time, and it would just fog up. So,
Yeah.
if the sapphire Gorilla Glass was no longer around, would you cease to
Mm,
have a cell phone, or would it just go back to being the one that scratches more easily? I
yeah.
think that's kind of more of the question.
Yeah.
The most
Mm,
practical applications that people relate to, that they can
mm,
touch in their everyday life.
mhm,
Some of the ones I can know of that I can share would be things like cutting bits. So, diamond tool bits. So a
mm,
lot of the cutting bits that are made. And I don't know if I can share the manufacturers, but a lot of times companies who've adopted SPS keep
mm.
that tight-lipped because it's a
Yeah.
strategic advantage for them compared to their competitors. So I have to be a little
Yeah.
careful. We know a lot of people who are using it, but cutting bits
Yeah.
is a good example. So when you're
Yeah. So
seeing a
used in
construction
the
site,
mining industry or to cut concrete
cutting
in construction works and so
exactly.
on.
Yep, things
Yeah.
like that. Cutting
Mm,
bits for just machining, which is a little less than everyday life, like we talked about. Like not everyone's familiar with cutting tools
mhm,
and things, but that's one area.
yeah.
Train brakes, train
Mm,
discs. So that was one of the first ones. So I didn't get into, and actually I have a slide I could show you the commercial ability of SPS. Actually, let me see if I can get to it while I'm talking. Um, Train breaks are there's two different ways you get into high volume SPSing, which is obviously what helps you get to commodity, which helps you get into the everyday
mm,
life of people. Oh no, it's not in this one, but essentially there's, oh yeah, here we go. So if you have a high volume application, which if everyday people are touching it, it means it's a high volume application.
mhm,
You can do it two ways. One is you oversize your machine and you go to a really, really large machine, and then you make multiple cavities, and then you can
mhm,
stack the parts inside of those cavities, like this one on the top here. So then every time
mm.
you sinter, you're making a dozen parts,
Yeah.
several dozen parts.
Yes.
That's one way of getting to high volume. The other
Mm,
way is actually through constraint mitigation, and that's what's called a tunnel type system. And essentially, this is a more complex version. These are almost exclusively in Japan.
mm.
But here, essentially, you're just breaking up that whole process. So you're working on 5 tooling sets at one time. And so while
Wow.
one is being pulled into vacuum,
Yeah.
the next one is preheating. And while that's happening at the same time, there's one that's being densified and actually sintering. And while that's
Mm,
happening, there's one or two being cooled down to a temperature so that they can be released. And so everything is moving in synchronous. And so you're processing all these dyes at the same time.
mm.
And if you really go crazy, each one of those dies has multiple parts inside of them, and so now you're really cooking,
Yeah.
and then you're making lots of parts. And
Mm.
that's one of the ways that they would do the train discs. So the high-speed trains in Japan, some of them are using discs, brake discs that are made with SPS as well.
Yeah.
Yeah, and then brake pads is another one that's more everyday. A lot of aerospace ones, some automotive, some motorcycle brakes. So they'll take the
Mm.
friction material and the brake pad liner and the backer plate, and they're bonded together. As I
Yeah.
mentioned, SPS is doing a lot of bonding as well.
Yes. Yeah, of course. Yeah.
Yeah,
Mm. Yeah. Thank you.
no problem.
Um, if people want to learn more, where would you advise conferences or should they just call you and make a new interview?
Yeah, yeah, exactly. I guess yeah, it depends. Yeah, what their interests are. Is it just purely academic and learning, or is it because they have a project and they're looking to work
Mm,
on it? So of course, our website www.calnanocorp.com would be a good place to start.
mm,
We have a lot of our information there. So if someone's interested in doing some work and we collaborate, we do probably 50 to 60 research contracts per quarter for everyone from one-man startups to international laboratories, defense contractors,
mm.
green energy startups, so literally everybody.
Yeah.
And then, yeah, there's more and more conferences. So every technical materials conference now has a growing portion of SPS and fast related kind of symposiums. And
Mm,
then there's some that are more focused on that. There's some SPS dedicated ones
yeah.
that are around. So it just
Mm,
really depends what area you're looking in. Some are more thin film related, some are more
mm.
bulk material related, some are more ceramics related. So, but it's everywhere if you look.
Yeah, it sounded like the most activities were in Japan and in Europe. Is it because the universities at the forefront in these areas?
It's a good question. I think Japan, I think in Japan, there was definitely two hubs of development that kind of started, and there's probably some inter-industry arguments on the inventors even, and then because I think there's a few different groups that maybe developed in parallel or something their own kind of
Mm,
ideas, and so the two hubs of invention were definitely in Germany and Japan, and so
mm,
they developed there. Why have they not spread as much? Yeah, I don't know if it's just a lag thing. Japan tends to, I don't know if it's a language barrier. Also, they do kind of their own thing with a lot of the technology and the conferences.
mm.
So that's obviously similar to the old Soviet, different obviously, but a lot of the old USSR stuff, they did a lot of good work that just
Yeah.
doesn't leave, the
Hmm.
area. So it's kind of been
Yeah, that's right.
isolated a little bit.
Yeah.
So similarly, I think it's just these hubs have had that. And so on the academic side, maybe they've been better at pursuing it on an academic level early on.
Mm,
Um, and I'm talking early being from the 60s and the 70s when this stuff really kind of started. But once
yeah.
you hit the like 90s into the 2000s, then I think, yeah, North America got into it and we're running. So
Mm,
now I think the largest machines are made in the USA now. One of
yeah.
my fellow directors of the company, Professor Enrique Lavernia, he's very tenured in this area through multiple universities. As I mentioned earlier, Idaho National Laboratories really done a lot of great work with one of those really mega units with Dr. Ruffner over there as well. So yeah, there's a lot of good units that are coming. So it's coming to fruition. I think it's the technology is really blossoming right now. I mentioned, when I departed the company originally, everyone was like, "Oh, that's nice, but it's just this."
Mm,
Now, when you sit at a conference, everyone comes by and goes, "Oh, this is the famous SPS. Yeah, I totally know
yeah.
about this." And it's like, "Oh, what a change a few years has made." So.
Yeah. Yeah. It's really growing. So I am really thankful. I learned something new today, and that was the purpose of the podcast. So thank you very much.
Hey, no problem. Thank you very much, Peter. And it was an absolute pleasure.